Welcome to today's presentation. In this video, we are going to talk about molar solutions. When 4 grams of a metal carbonate was dissolved in 160 cubic centimeters of 1 molar hydrochloric acid, and then the resultant solution diluted to 1 liter, 25 cubic centimeters of this solution required 20 cubic centimeters of 0.1 molar sodium hydroxide solution for complete neutralization. Calculate, Roman 1, the number of moles per liter of excess hydrochloric acid that reacted with sodium hydroxide. Roman 2, the number of moles per liter of acid that reacted with the carbonate. Roman 3, the number of moles of carbonate that reacted with the acid. Roman 4, the formula mass of the carbonate. And finally, Roman 5, the atomic mass of the metal M. So for the first part, we are to determine the number of moles per liter of excess hydrochloric acid that reacted with sodium hydroxide. In the equation, we are told that 25 cubic centimeters of the diluted solution required 20 cubic centimeters of 0.1 molar sodium hydroxide solution for complete neutralization. Well, let's consider this first. When we have sodium hydroxide and hydrochloric acid reacting, then the equation for the chemical reaction becomes this. And therefore, from this, you can see that the mole ratio for sodium hydroxide and HCl is 1:1. That is 1:1. And that means that we can tell the number of moles of HCl that reacted if we know the number of sodium hydroxide that reacted. So we are going to determine the number of moles of sodium hydroxide. That is the number of moles that reacted with HCl here. So we'll say number of moles of sodium hydroxide is molarity times volume in liters, and molarity here we're given as 0.1 molar, 0.1, that is moles per liter, times the volume in liters. So the volume that was reacted is 20 cubic centimeters. So 20 cubic centimeters in liters we divide by 1,000, and that should be 0.02 liters. And this should give us 0.002 moles. We had noted that the mole ratio for sodium hydroxide and HCl that reacted is 1:1, and that also means that the moles, that is number of moles of hydrochloric acid that reacted here, is also 0.002. But we need to note that 25 cubic centimeters of the solution required 20 cubic centimeters of 0.1 molar sodium hydroxide for complete neutralization. So that simply means that the 25 cubic centimeters contained 0.002 moles. But remember, we are required to determine the number of moles per liter. Therefore, we'll say, how about 1,000 cubic centimeters? What will it give us? So if we cross multiply, we are going to have 1,000 times 0.002 over 25, and that should be 0.08 moles per liter. So this is the number of moles per liter of excess hydrochloric acid that reacted with sodium hydroxide. So it is excess because initially we had 4 grams of the metal carbonate dissolved in the hydrochloric acid, that is 160 cubic centimeters. So this reacted with some of the hydrochloric acid, and then the excess hydrochloric acid is the one that reacted with the sodium hydroxide. So that is for Roman 1. For Roman 2, we are required to determine the number of moles per liter of acid that reacted with the carbonate. Now, we need to take note of this. the number of moles, that is of HCl, reacting with the carbonate should be equal to the original number of moles of HCl minus the number of moles of HCl reacting with sodium hydroxide. So from this equation, we are required to determine the number of moles per liter of the acid which reacted with the carbonate. So we are going to determine the number of moles of HCl, the original number, and that we obtain as, we'll multiply the molarity times the volume in liters. So the molarity we are given as 1 molar, so that is 1 mole per liter. And then the volume of hydrochloric acid originally is 160 cubic centimeters. And 160 cubic centimeters in liters, we divide by 1,000, and that will be 0.16 liters. And that should give us 0.16 moles. And then once we're done with that, we'll have to subtract the number of moles of HCl that reacted with sodium hydroxide. And that we'd already obtained up here. The number of moles of HCl that reacted with sodium hydroxide is this. So we subtract 0.08 moles per liter. And that should give us, so here we have 0.16 minus 0.08, and that is 0.08 moles per liter. So that is the number of moles per liter of acid that reacted with the carbonate. For the next part, we are required to determine the number of moles of carbonate that reacted with the acid. So we are going to write the equation for the reaction between the metal carbonate and HCl. And then from here we can see that the mole ratio for the metal carbonate to HCl is 1 to 2. 1 to 2. We can therefore argue that if 2 moles, that is of HCl, represents 0.08 moles per liter, that is the number of moles that reacted with the carbonate. How about 1 mole of the metal carbonate? So cross multiplying will have 1 times 0.08 over 2, and that is 0.04 moles per liter. So that is the number of moles for the metal carbonate that reacted with the acid. For Roman 4, we are required to determine the formula mass of the carbonate. The relative formula mass, also known as the molar mass, is given as mass over number of moles. And the mass of the carbonate that was dissolved was 4 grams. And then the number of moles that reacted, we've already gotten. That is 0.04 moles per liter. 0.04 moles per liter. And then when you divide this, we get the relative formula mass as 100. Lastly, we are required to determine the atomic mass of the metal M. Now, the molecular mass for the metal carbonate, we already determined as 100. That is from the previous part. We have it as 100. So that means that if we consider this, the atomic mass for M, let's have it as M, plus atomic mass for carbon, that is 12, plus atomic mass for oxygen is 16, and the 3 atoms, so we multiply by 3, and then we equate that to 100. So from this equation here, we'll be able to get M, which will be the atomic mass of the metal M. So the left hand side we have M plus, so here we have 48, 48 plus 12, that is 60, and then you equate it to 100, and therefore M becomes, so 60 goes to the right hand side, 100 minus 60, we get 40. So the atomic mass of the metal M is 40. And with that, we come to the end of the solution to this problem. Thank you for watching. See you in the next video.